Before we talk about 45, 45, 90 triangles, I want to introduce one other triangle idea to you that you may not have seen in the past. To do this, let's look at this triangle. So I got this guy right here. Now, I'm going to label his side lengths A, B, and C. Now, just so you know, normally we label side lengths with lowercase letters, angles with uppercase letters when we're talking about them being paired together. Now, here's the thing I want to introduce to you. Did you know that angles and sides in a triangle are connected? They're paired. Specifically, the angle across from that side is connected. Let me show you what I mean by this. If I look at this triangle and I ask you, which of these sides is the shortest, is the smallest? You would quickly tell me A. A is the smallest side. Well, that means if I go across from A, the angle across from A will be the smallest angle. See that relationship there? The smallest angle will be across from the smallest side. And that's why we pair them lowercase a, capital A. Now let's notice another thing. Understanding this relationship then, which of these remaining two angles will be the biggest? Or you could also ask, which of the remaining two sides will be the biggest? Well, we know that C is going to be the biggest side because C is across from the biggest angle. So because C is across from the biggest angle, that makes it the biggest side. So that means B would be in the middle of them. But that's how we talk about angles and sides, is the smaller the side, the smaller the angle, the bigger the side, the bigger the angle. Now, understanding all of this, let's look at our 45, 45, 90. In our 45, 45, 90, we have two angles that are identical, that are the same, which means the sides across from those angles will also be the same. In geometry, we usually label this with tick marks. These little tick marks show that these side lengths will be the same length, the same amount. I don't know how long they are. They might both be 5 inches long. They might both be 3.2 inches long. I don't know. But I know that whatever one side is, the other side will be the same because it's a 45, 45, 90. Now we have a special word for this. We call this isosceles. An isosceles triangle is a triangle that has two sides that are the same length. Now, like I said earlier, I don't know what these side lengths are. I just know they're the same. So let's go ahead and just call them both X. That way I don't know what they are, but I do know they're the same length. They're both X long. Let's say I then told you I want you to find the length of the third side. Don't you have a tool in your toolbox that says if you know two of the sides, you can solve for the other side? Hopefully, you thought of Pythagorean's theorem. Pythagorean's theorem is the way that we take, if we know two sides of a right triangle, we can solve for the third side. Now, little side note, Pythagorean's theorem only works on right triangles, no other triangle. So I have my Pythagorean's theorem here. A and B are the smaller sides. C is your hypotenuse. So it doesn't really matter which side we put in A, which side we put in B, that's interchangeable, but we need to make sure the hypotenuse always goes in C. Now, I know that the smaller sides are both X, that's what I called them, so I'm going to put that in there. And then I'm going to solve this for the hypotenuse, so solve for C. I know x squared plus x squared is 2x squared, square root C, so that I can solve for C. I get C is the square root of 2x squared. Now, you may remember from earlier math classes, maybe not, that you can split up square roots over multiplication and division. The reason I would do this is so that this square and that square root cancel, and I get c is the square root of 2 times x. So that means my hypotenuse here is the square root of 2 times x. Now this is a really big idea. This means it doesn't matter what number these sides are, we know that this hypotenuse will be square root of 2 times that number. So let's say I gave you a triangle, I told you it's a 45, 45, 90, and I told you that this side length is 5. Then you would know that this one is also 5 because of the isosceles, and you would know that this is square root of 2 times 5, because that is always the hypotenuse based on those sides. And it doesn't matter what number it is. Let's say I told you this side was 9.3. Then both of these are 9.3, and this one is square root of 2 times 9.3. And that works for every single 45, 45, 90 triangle, this awesome pattern that we have here. Now this pattern is going to be really important for us to memorize. So let's write down these patterns that we're seeing. The first pattern we know is that these two sides will be the same length. That's our isosceles. The next pattern I see is that if I have this side, if I give you this side, and I want the bigger side, I take the smaller side and I times by root 2, and that will give me the bigger side, which should make some intuitive sense. If you have a smaller side and you want to make it bigger, you multiply by a number to make it a bigger length. So whatever this side is times by root 2, that gives you that side. And this brings us to an important question. What if I wanted to go backwards? What if I told you this side is 10 and I wanted you to find these two sides? Well, if we multiply by root 2 to make it bigger, then all you would have to do is divide by root 2 to make it smaller. So whatever number is here, divide it by root 2, and that will give you these numbers. So let me give you an example. Let's say, like we said earlier, this side length is 10. That means these two would both be 10 divided by root 2. That's how we go the other direction. But that works for every single 45, 45, 90 triangle. No matter how big or small it is, no matter what one of the side lengths start as, to get bigger, we times by root 2. To get smaller, we divide by root 2. And it makes it really fast to solve these triangles. Now, let's actually get to what we were talking about earlier with SOHCAHTOA and trig. We know that the trig functions for every 45, 45, 90 triangle will be the same because they're similar triangles. So let's take a second and label this triangle. I go across from the right angle. That's my hypotenuse. And then let's say for the sake of this problem, we're going to focus on this angle. It doesn't particularly matter because they're both 45, but let's just pick that one so we're all on the same page. So that means opposite is across from that angle. There's my opposite side. And adjacent is what's left. There's my adjacent side. So what I want you to do is come down here now and do my 6 trig functions for this angle that I'm focusing on. I'm focusing on that 45. And then we'll take those 6 trig functions and flip them. To get the other ones. So let me do the first one with you so you can kind of see what this looks like. I know that sine is opposite over hypotenuse. That's my SO in the SOHCAHTOA. My opposite this time is x. That's the length of the opposite side. And my hypotenuse this time is square root of 2 times x. That's the length of my hypotenuse. And you'll notice my x's cancel, and I get 1 over square root of 2, which is left. So that means the sine value for every 45-degree angle, doesn't matter how big or small the triangle is, will be this fraction because of that similar triangle idea. In fact, you could put sine of 45 in your calculator, and this is what it's going to give back to you. Now, little side note, this may not look exactly like what your calculator gives you. Your calculator may give you root 2 over 2. So let's do a little side thing right here. If you take 1 over square root of 2, and you do a process called rationalizing the denominator. Essentially, mathematicians forever ago decided we shouldn't have roots in the denominator, so we're going to make that illegal. So this process called rationalizing the denominator gets rid of the root in the denominator. Here's how it works. You multiply by what the root is on top and bottom, and then solve. So multiply across on top, 1 times root 2 is root 2. Multiply across on bottom, root 2 times root 2 is root 4, or root 2 squared, which is just 2. So essentially we're saying that this number and this number are exactly the same. In fact, you could put both of these into your calculator. They will give you the exact same decimal. We're just writing them differently. This one makes sure there's no roots in the denominator. This one says, hey, roots in the denominator are chill. We're just going to leave it. Now, for 1060, Slick has told us that you do not need to rationalize the denominator. So leaving your answer like this is perfectly fine. You do not need to do this process to it. Some teachers are different. Some colleges are different. Some will make you do it. Some don't. However, the end of the story is your calculator gave you this. That is the exact same number as this. So sine of 45 is that. And that works for every single 45-degree angle. Now, here's what I want you to do next. I want you to do the exact same thing for cosine and tangent, and then flip them all to get the other 3, using everything we've labeled with our triangles so far. Make sure you simplify them to get your final fraction. Pause the video, finish out the rest of these, and then come back to check your work. Let's check your work. So this is what I got for my cosine and my tangent, and then I went to flip them all, and this is what I got. Remember that this is technically 1 over 1. Everything's over 1. So when we flip it, we still get 1 over 1. So these are your trig values for every single 45-degree angle. It doesn't matter how big the triangle is, how small the triangle is. If it's a 45, 45, 90, these are the trig fractions that you're going to get from that triangle. So you can start to see why we talk about this pattern. It comes up a lot. It works for a lot of different triangles. The other special right triangle we talk about is a 30, 60, 90. So that's what we're going to talk about in the next video, how to find the trig ratios for that other special triangle.